In Theorem 4.5 here we have the definite integral as the area of a region. If the function f is continuous and non-negative on a closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x is a and x is b is given by this. Area equals the integral from a to b of f of x times dx. And this is summed up here in this picture. We have our function f. It is continuous, it's non-negative, and we are looking at the area bounded by the x-axis and the two lines x equals a and x equals b. So we're looking at this as the area under a curve. So you can use the definite integral to find the area of a region bounded by the graph of the function, the x-axis, and our two x lines, x equals a and x equals b. As an example of Theorem 4.5, consider the region bounded by the graph of 4x minus x squared and the x-axis as shown in the figure. This shape is just a downward opening parabola. So here we have our high point at 4, and we have a downward opening parabola going through the origin and crossing the x-axis at 4. Because f is continuous and non-negative on our closed interval from 0 to 4, the area of the region is, we have our integral symbol from 0 to 4, our left and right endpoints, of our function 4x minus x squared times dx. A straightforward technique for evaluating a definite integral such as this will be discussed in the next section. For now, however, you can evaluate a definite integral in two ways. We can use the limit definition, or you can check to see whether the definite integral represents the area of a common geometric region, such as a rectangle, a triangle, or a semicircle. And that's what we're going to do here in example 3. We're going to start looking at these and figuring out that they are just common geometric shapes that we're used to and that we already have a formula for. So what really helps here is we sketch the region corresponding to the integral and then evaluate the integral using a formula that we already know. So what I'm going to do here is set up an x and y axes to use on all three of these. So what do we have in the first one? Our function is 4. And seeing it in this notation might be a little confusing. Remember, this is our function, f of x equal or y equals. So y equals 4. What kind of shape is that? If we graph that on the plane, that's just a horizontal line. So here's 1, 2, 3, 4. We have a horizontal line at 4. And we're looking at that bounded by the x-axis, and our lower and upper limits are 1 and 3. So 1, 2, 3. Here's the region that we're interested in. I'll use dotted lines here and here. We want to find the area of this region. And hey, that's just a rectangle. Let's see. The width of the rectangle is 2, and the height of the rectangle is 4. So we have a rectangle equals length times width, or 2 times 4, which is 8. No calculus required. Down to part B. Again, here is the function we're dealing with. And what is that? Y equals x plus 2. Well, it's just a line. Y equals mx plus b. So we know we have y-intercept here at 2. Y-intercept at 2. And we have a slope of 1. And we're looking here from 0 to 3. So we're going to start at the origin, and then 1, 2, 3. And the slope is 1. So if we go up 1, over 1, up 1, over 1, up 1, over 1. So here we are. So we got 1, 2, 3, 4. That's 5. And here's our line. And we're looking at that region bounded by the y-axis, the x-axis, and 3. So what shape do we have here? Well, that's just a trapezoid. It's sort of on its side, but we have a trapezoid. And the area of a trapezoid is 1/2 the height times the sum of the bases, b1 and b2. And our bases are going to be these sides. So our bases are 2 and 5. So in these parentheses will be 2 plus 5. and we're going to have half the height, and the height is this way, which is 3. So we got a half times 3 times 7, and that turns out to be 21 halves, or 10.5 units squared, whatever units we're dealing with. Okay, the last one here might not look so recognizable unless you have a very good memory back to pre-calc. Remember, this is our function, y equals, and then we have this square root 4 minus x squared. What happens if I square both sides? Y squared equals 4 minus x squared. And let's get both variables on the left. If I add x to both sides, I get x squared plus y squared equals 4, which is 2 squared. What does that ring a bell? What does that look like? X squared plus y squared equals r squared, or it's just the area of a circle. We have the formula for a circle. I'm going to need to move this over here a little bit. It's a circle centered at the origin, and its radius is 2. So what we have is this. Excuse that drawing, that's just a terrible semicircle. But you get the idea. We go from -2 to 2, that's our lower and upper limits, and our height is going to be 2, and we just have a simple circle. What's the area of a circle? Pi r squared. Pi r squared is a circle. We're only interested in half of it. So 1/2 times pi times 2 squared, or 4. So we're going to get half of 4 is 2 pi, and that is approximately 6.28, or twice of 3.14. So no calculus required. We just had to identify from our function what kind of geometric shape we were dealing with, and we found the area under that curve. Definite integrals have some different properties. So the definition of a definite integral of f on the integral from a to b specifies that a is less than b. Now, however, it's convenient to extend the definition to cover cases in which a is equal to b, or a is greater than b. Geometrically, the following two definitions seem reasonable. For instance, it makes sense to define the area of a region of 0 width and finite height to be 0. In these properties here, we have this first definition. If the function f is defined at x equals a, then we define the integral from a to a of f of x dx equals 0. And that makes sense if we go back here to this first one, where we just had a horizontal line at 4. So here's our function, here's our horizontal line. Instead of from 1 to 3, what if we had the integral? You know, from 1 to 3 we found the area of a rectangle. What if the upper and lower limits were the same from 1 to 1? What if we just do a straight line there and said what's the area of that line? Well, if you remember back to geometry, a line is infinitely thin. It has length but no width. So that would have no area. You know, that's all this first one is saying. If the lower and upper limits are the same, no matter what the function is, the area is going to be 0. And in the next one, if f is integrable from a to b, then we define, if we have b to a of our function f of x, what we can basically do is switch the upper and lower limits. I'm going to put a at the bottom, move b to the top, and to make that still balance out, we just have to put a negative sign out front. So switch your upper and lower limits, put a negative sign out front, and all is good. Down here in example 4 are just a couple applications of what we just saw in that definition box. In part A, because the sine function is defined at x equals pi, and the upper and lower limits of integration are equal, you know, we have the integral from pi to pi of sine x times dx. Well, that's just going to be 0. Again, it doesn't matter what the function is. If your upper and lower limits are the same, then the answer, the area there is going to be 0, because we're basically just trying to find the area of a line. In part B, the integral from 3 to 0 of x plus 2 dx is the same as that given in example 3b, except that the upper and lower limits have been interchanged. Because the integral in example 3b has a value of 21 halves, we could just write this integral with the upper and lower limits switched is just the negation of that, negative 21 halves. So here our lower limit was 3, upper limit 0 of x plus 2. Well, if we switch the upper and lower limits, we got to balance that by putting a negative sign out front. Now it's the integral from 0 to 3 of x plus 2. And we'd solve that just like we did in example 3, and we got 21 halves. But now we've created this negative sign out front by switching our upper and lower limits. So that would be negative 21 halves. Okay, in the figure above, the larger section, we have our integral from a to b. This larger region can be divided at a point C in the middle. So we're going to pick any point C in the middle, and we subdivide our region into two subregions. Because the line segment has 0 area, it follows that the area of the larger region is equal to the sum of the two smaller regions. So if we look down here in theorem 4.6, if f is integrable on 3 closed intervals determined by a, b, and c, then the interval, or the integral from a to b of the function, that's this entire distance, we can break it up into two smaller regions. So changing the integral from a to b, we now have the integral from a to c of f of x dx. That's the first piece. And then we add to that, here we left off at c. This integral picks up at c, the integral from c to b, where we finish off our region under the curve, from c to b of f of x dx. This is just saying if we take the two small pieces and add them together, we get the big one. And that's it. So, example 5. Let's use that additive property, additive interval property. So, again, I'm going to need xy axes here. We're looking at the interval, or the integral from negative 1 to 1. So here's a negative 1 to 1 of the absolute value of x times dx. Okay, what does the absolute value of x function look like? Do you remember that from pre-calculus? Remember the absolute value function, just sort of make it a V-shaped. We come down, we hit the origin, and we bounce back up. That's the absolute value of x. Absolute value is never negative. We've never dipped below the x-axis. We've never gone into negative y territory. So what we want to find from negative 1 to 1 is the area under our curve. So if we want to use this additive interval property, from negative 1 to 1, we're going to break up right here at the origin. So our first interval goes from negative 1 to 0, and that is just, this line on the left here is negative x dx plus the integral from 0 to 1. So, originally we went from negative 1 to 1, now we're going from negative 1 to 0, and then picking up there 0, and finishing off to 1. Now this line over here is just x dx. And these are just two triangles. First one is a triangle, the second one is a triangle. They are both, remember, area equals 1/2 base times height. So the area of each triangle separately is 1/2. The base is 1. The height is 1. So the area of each triangle is 1/2. The triangle on the left has an area of 1/2. The triangle on the right has an area of 1/2. So this one here is 1/2, plus the area of the second triangle is also 1/2. 1/2 plus 1/2 is 1. Okay, some more properties of definite integrals. Because the definite integral is defined as the limit of a sum, it inherits the properties of summation that were given earlier in the book. So f and g are integrable functions on the interval from a to b. K is just a constant. Then the functions k times f and f plus or minus g are also integrable on from the interval from a to b, and the integral from a to b of the constant times f of x dx, we can drag the constant out front. So here we just pull the k out front. K times the integral from a to b of our function f of x times dx. And here we have the integral of a sum or difference. we're taking the integral of a function f of x plus or minus the other function g of x. It's almost like we distribute the integral sign. We can break it apart into two different integrals. The integral of the first part from a to b of f of x dx, plus or minus, whatever the case may be, the integral from a to b of g of x dx. Note that for property 2 of this theorem, it can be extended to cover any finite number of functions. You know, we could have the integral from a to b of f of x plus g of x plus h of x and break that into 3. Or if it was 4 or 5 or 6 functions, this property still holds. So here in example 6, there are some homework problems, I believe, like this. We're evaluating the integral from 1 to 3 of a 3-term function. Minus x squared plus 4x minus 3. We want to evaluate this using these following values. The integral from 1 to 3 of x squared dx we know has this value. The integral from 1 to 3 of x times dx equals 4. The integral from 1 to 3 of 2, or from 1 to 3 of just dx, or 1 dx, is equal to 2. So let's sort of apply these theorems. We're going to bust the original one apart a little bit. So let's see what we can do here. Here's our, let me slide this up. We still have to be able to see those values. So if we break this up, we're going to have our integral from 1 to 3 of negative x squared plus the integral from 1 to 3 of 4x minus the integral of 1 to 3 of 3. And I did forget in there all of my dx's. Let me slide this over a little bit. Oops. I did forget. When you do break these up, you do have a dx. That differential goes with each. Okay. Now let's see. You know, we have values for x squared and x and dx, so let's make it look a little more like that. Here we have our integral from 1 to 3. Well, we have that negative. Let's pull that negative out front. Negative the integral from 1 to 3 of x squared dx. Plus, here we have a 4x. You know, let's pull the 4 out front. 4 times the integral 1 to 3 of x dx. And then here we have just a constant, a 3. Let's pull that out front. Negative 3, or minus 3, the integral from 1 to 3 of dx. Now we can sort of plug in the stuff that we have above. So, this integral from 1 to 3 of x dx, they told us was 26 thirds. We have a negative out front. Negative 26 thirds. Plus 4 times this integral from 1 to 3 x dx is equal to 4. So that's going to be times 4. Minus 3, this integral from 1 to 3 of just dx is equal to 2. So what we have is negative 26 thirds plus 16 minus 6, and that all turns out to 4 thirds. Now, if f and g are continuous on the closed interval from a to b, and f of x is always less than g of x, but still greater than 0. You know, f of x is always under g of x, but still positive. It's still above the x-axis. For all the x's in the interval from a to b, the following properties are true. First, the area of the region bounded by the graph of f and the x-axis must be non-negative. So here's our function. It's between f and the x-axis. That is definitely non-negative. Second, the area must be less than or equal to the area of the region of the graph bounded by g and the x-axis. So the area under g is always greater than the area just under f. And that makes sense geometrically, you know, because g is always higher than f. These two properties are generalized in theorem 4.8. There is a proof in the back of the book. So here in theorem 4.8, if function f is integrable and non-negative on our closed interval from a to b, then it is always greater than 0. 0 is less than our integral. It's always positive. If f and g are both functions and are integrable on our closed interval from a to b, where f of x is always less than or equal to g of x for all x values, then the integral of f of x is less than the integral of g of x. And that is the end of section 5.3, Riemann sums and definite integrals. And the next section, section 5.4, is the big one. We will find the fundamental theorem of calculus, the FTC, one of the greatest mathematical discoveries of all time.